Okay, we're starting right on time, as is our custom. So this is our annual PH lecture, which was established by Paul Hertlendy, who is our guest here this afternoon. Paul was a very much loved member of the Smithsonian National Board and came to be known as the Poet Laureate of the Smithsonian National Board. And it was through that affiliation, not the poetry, the National Board part, that we came to know him. And he took an interest in astronomy, and took an interest in particular in how we recognized the careers of people early in their development. And as a result, he wanted to recognize a young scientist, and we were never very precise about what young actually meant. But a young scientist at the Center for Astrophysics who is on a trajectory for very significant astronomical career. So actually, Paul offered to make a few remarks, so I'll just hand the floor and the mic to you. So this.
Thank you. Great pleasure to see you all here today. And I just want to say the SAO does fantastic work, and the people here in this room will probably not be visiting the first planet believed to have human life or life of any sort. However, it'll be people from the SAO that will probably be putting out the signposts to show people how to get there.
Well, we'll try. So anyway, now let's move on to our speaker and our prize winner. So Reinout van Weeren is a native of the Netherlands, where he was educated, got his PhD at Leiden. He's actually been here for about 5 years now. And he's been in the high energy astrophysics division, where he's worked with X-ray data and radio data. He's been a very panchromatic scientist. He's going to speak to us today on the largest particle accelerators in the universe. And before he starts, I'd like just to hand this certificate to you in recognition. And if we get a picture taken briefly. Okay, you're on. Thank you.
Yeah, thank you for giving me the opportunity to talk here, and also thanks for Paul for coming here all the way. So today I will talk about the largest particle accelerators we have in our universe, and this is of course not work I've done alone, so I list here at the bottom here all the people who are involved in this work. In particular, we have the LOFAR Surface Key Science Project in the Netherlands, but also many people here at CFA who work on Chandra X-ray data. And it is through this combination of radio and X-ray observations that you can really make very interesting discoveries. So I will start my talk about galaxy clusters, because that's kind of one of the main topics. So we all know galaxy clusters are the largest gravitationally bound objects in the universe. And this is an optical image of the galaxy cluster Abel 2744. So here in all the kind of yellow specks here are essentially the galaxies which belong to this cluster. And you can already see there are several different subconcentrations present in this cluster. Now this is in the optical. You get a very different view of a galaxy cluster if you move to X-ray wavelengths. So this is an image of the same cluster here taken with the Chandra X-ray Observatory. And here you see essentially the hot gas with energies of keV roughly. So that's roughly 10 to 100 million degrees Kelvin. And then this gas emits thermal brightness which you can then detect with Chandra. And this we also call the intercluster medium. So this is essentially the hot gas between the galaxies in the cluster. Now again, you can obtain a very different view of this cluster if you go to the radio band. So this is a radio image again of the same cluster made by a student here, which was here, an exchange student with Southampton. This is Connor Pierce, who made this really fantastic, very deep radio image of this cluster. And what we see here is something different. So what we see here are cosmic rays and magnetic fields, essentially the combination of the two. So if you have cosmic rays, so very energetic particles, and magnetic fields, you get synchrotron radiation. And that's radiation you can detect with the radio telescope, so in the megahertz or 2 gigahertz frequency range. So not so far from where we essentially our mobile phone works, or for example FM radio. And the nice thing about synchrotron radiation is also that you can actually directly study the magnetic fields by looking at the polarization of the radio signal. So here I plot essentially the electric field vectors, which is perpendicular to the magnetic field vectors, on top of this kind of source here. And this shows that magnetic fields in a cluster roughly have a strength of a microgauss. So to compare with the Earth magnetic field is about a Gauss. So these magnetic fields are extremely weak in these galaxy clusters, and also because the densities are extremely low. So one of the main questions is now, where do these cosmic rays come from? Because they're quite special, right? They're really relativistic particles. So how can you accelerate these particles? Where are they accelerated, for example, in the cluster? And one of the other important things I have to tell you, characteristics of a radio source, is the radio spectra. So radio spectra essentially tells us how bright a radio source is as a function of frequency. And radio spectra are typically quite boring. So they typically have power law shapes. And the slope we call the radio spectral index. So we can measure the slopes by taking observations at, for example, at 2 frequencies. And then we know what the spectral index is. And typically I talk about flat and steep spectra. Steep just means that sources get much brighter at low frequencies. So these are low frequencies, so sources get much brighter. While flat spectra have a relatively more constant flux as a function of frequency. So here you see the frequency axis. Now, galaxy clusters are not alone in the universe. They're embedded in much larger structures, of course. So that's the cosmic web. And this is a simulation essentially showing the dark matter distribution in our universe from the cosmic web. And these galaxy clusters sit at the nodes essentially of these filaments of the cosmic web. So here, this is an example of a galaxy cluster here in visible light. This is kind of like a toy cartoonish picture. And again, here we see an observation done with radio and X-ray satellites and radio telescopes, where we see an example of such a galaxy cluster here, where we see the gas in blue, the X-ray gas, and the radio emission here in red. So now the idea is that we kind of have to accelerate these particles in this cluster. So how are we going to do this? And the main idea is basically that we know that galaxy clusters form by collisions of smaller structures in our universe. So here I show an animation of a galaxy cluster merge event, where you basically take 2 big balls of gas, you collide these balls of gas, and then you form 2 outward propagating shockwaves. And now the idea is that in these shockwaves you can start accelerating particles. And now you can see a kind of the resemblance with this image here. Here you see this radio arc, and we think that this radio arc essentially traces this shockwave as it's generated when this course of the cluster passes. That's the basic idea what we have. Of course, this is just an idea. We have to prove this. So there's actually a lot of interesting astrophysics you can do with galaxy clusters. So it's interesting to know that if we start with the cosmic microwave background, so then we have the first galaxies form in the universe, for example, shown in the Hubble Deep Field. And then finally we have galaxy clusters. So galaxy clusters are actually very young objects. They're still actively forming. They kind of form after the first galaxies. So only kind of the last couple of billion years we really formed these really massive galaxy clusters. Before that, these structures did not exist. So they formed really late in this process of structure formation. And essentially galaxy clusters are still growing. This process has not stopped yet. And an famous example, for example, of a colliding galaxy cluster, so a galaxy cluster which is merging and growing, is, for example, the Bullet cluster here. And this was also work here done by Maximon, I think, when he was still at the CFA. So there are a lot of interesting physics you can do. So one I already talked about is like particle acceleration and shocks and turbulence in clusters. So I will mainly focus on this, but there are many other interesting things. For example, we also know that galaxy clusters are large gravitational telescopes. They lens background objects, so you can also study them. You can use them to detect really faint galaxies. And also galaxy clusters are very sensitive probes of cosmologies. If you count the number of galaxy clusters as a function of mass and redshift, you can determine cosmological parameters. It's interesting to note that if you look at the mass budget of a galaxy cluster, then most of the mass of a galaxy cluster is in the form of dark matter, which we cannot really directly see. And about 10% is in this hot X-ray gas. And only a very tiny fraction is actually in the galaxies. So in this talk here, we will mostly focus on this ICM here, this 10% of the mass of galaxy clusters. So what is the outline of the talk? So I will first give an introduction and some background. So basically how this field has developed over the last 20 years roughly. And then show some very recent results we obtained with new radio telescopes. I'll end with a summary and give an outlook what we can basically do in the next 10, 20 years, where we have to go. So again, going back to this image of this galaxy cluster Abell 274, this radio image here. So you can already see there are many different kind of structures in this image. So for example, we have tilt radio galaxies here. I will talk about that later, that are essentially radio emission directly associated with a supermassive black hole in the center of a galaxy. But the main thing is we see this kind of central radio emission at the center of the cluster where the X-ray emission is, and we see this kind of radio emission in the outskirts. So we classify the radio sources in galaxy clusters basically in two big groups. So we have radio relics, we call them relics. They're really these elongated sources. They're highly polarized, and they have kind of this filamentary morphologies, and they're always really far in the outskirts of the cluster. In the center of the clusters, we have radio halos. They more or less follow the X-ray emission from the ICM. And they're typically unpolarized, and all of these kind of diffuse sources are typically found in merging clusters, again, showing that probably there's a relation with shocks and maybe also turbulence generated by the merger. Now, one important thing to consider is that if you have a cosmic ray electron in a galaxy cluster, its lifetime is actually quite short, speaking if you compare to the galaxy cluster lifetime. So these electrons, they only radiate synchrotron emission, what we can observe, for about 10 to the 8 years or less. And that basically means that we cannot, for example, produce these cosmic rays in black holes and then, for example, like diffuse them out in the large volume of a galaxy cluster, because simply the time that takes is too long. These particles live only for 10 to the 8 years, and you do not have enough time to form this really large megaparsec size structures. So these particles have to accelerate it really in this hot gas in the cluster, not in galaxies itself. At least that comes from this simple argument. Now there's one other kind of important class of radio sources, which was actually much discovered before radio emission from galaxy clusters, and that's the radio emission from supermassive black hole. So this is a very nice example of the radio galaxy Hercules A. So here we have an optical background image from the HST, Hubble Space Telescope, where we see these jets being launched into these giant, essentially, radio lobes. And in red, this is essentially the synchrotron emission here again. So this is a different class of radio sources where the particles are accelerated at the supermassive black holes. And then they go in the jets and they form these really giant lobes. Now in clusters, galaxy clusters, we have galaxies, of course, so we also have these kind of sources. However, they look a little bit different than what you see here. So they look much more disturbed. So this is an example of such a radio galaxy in this cluster, where the galaxy is sitting here, then two jets are being launched, kind of forming backwards. And the idea is that essentially these radio galaxies then move through the gas of the cluster, causing these jets to be bent backward. And here you see such a sequence. This is a nice work was done by George Miley already in the 80s, where he proposed essentially this is a normal radio source, and when this source is in the ICM of a cluster, and depending on how quickly it moves, this jet starts bending backwards. So that's why these radio galaxies in clusters look typically quite different from radio galaxies in the field, which are much more symmetric. So in the cluster, they really have funny forms, probably because all the interaction with the gas. Okay, so what are the big questions we have here? So, of course, the main question is like, how are particles accelerated in the ICM? So I already told you that probably shocks and turbulence play a role here. Also, we have the question is, what is the efficiency of this acceleration mechanism, and what is the maximum energy we can reach with this kind of particle accelerators, which is an interesting question. And also, what particles are really accelerated? For example, are these the particles in the X-ray gas, or maybe do the radio galaxies also play a role, because they, of course, fill the volume of an ICM maybe with fossil relativistic particles. And then what are the properties of the shocks in clusters and the magnetic fields, because they, of course, play a key role in this acceleration mechanism. And finally, also, what is, for example, the ICM energy belt? This is very important because cosmic rays and also magnetic fields, they contribute to a little bit of the pressure in the ICM. And if you want to, for example, use clusters as cosmology, as really precision cosmology, and you want to know the mass of a cluster at the 1% level, for example, you have to worry about the energy content in these cosmic rays and magnetic fields. And also there's the general picture is like essentially how important are these non-thermal components as a function of cluster mass, and how does this evolve over cosmic time when galaxy clusters essentially grow. This is still, we essentially don't know very little about these things. So I always like to show this picture, kind of show like how far we have come in the last 20 years. So this was one observation of a galaxy cluster done 20 years ago by Ger de Bruin, who is a radio astronomer in the Netherlands working with the Westerbork telescope. And he took this image of this galaxy cluster and he printed this out because he found it quite interesting. It looked kind of like odd. It had this kind of weird tail-like shore. So he asked the question, maybe this was a big AGN with a giant tail. And he printed this out and he left it on his desk for 20 years. He kept it, but he never did something with it until we observed this source. So how far do we have come now? We can now essentially make images of the same object. And this is work done by Gabriella, who's sitting here in the room, who's a PhD student. We can now make this kind of very detailed images of this object. So we can really now study these sources in detail. This is really an enormous improvement over these studies which were done 20 years ago. And I always like to show the comparison in size, because I said these are the largest particle accelerators in the universe, so I just show here the size roughly the Milky Way. I think it's actually even a bit smaller. So these are really giant structures in the sky. And if I would plot the full moon, which I have not shown, this structure actually spans a quarter of the full moon on the sky. So it's really a big structure. It's a couple of billion light years away, but it's really big. If you had radio eyes, you could see this, easily see this. Okay, so now we'll go a little bit more detail in the relics first. These are the sources in the outskirts. So how can we accelerate these particles? That's the main question we have. And there are several mechanisms. So the first one is what we have is diffusive shock acceleration. We know that this works, for example, in supernova remnants, so essentially the remnants of that star which exploded, and in these shocks you can accelerate particles, and that probably happens via this diffusive shock acceleration. So there you have really high Mach number shocks, so Mach numbers of 10 or even much more. And in clusters we think we have actually not such strong shocks, so the Mach numbers are more like between 1 and 3. So the question is, can we actually accelerate shocks in clusters really, because the shocks are not so strong? That is an important question we have. It's interesting to note that in this case there's a direct relation between the shock Mach number and the radio spectral index. So we can, for example, measure the shock Mach number from X-ray observations, and then we can compare that to the radio spectral index, the slope in the radio, to, for example, to check if this relation holds. And that would be in support, for example, for diffusive shock acceleration. Now there's an alternative mechanism, and that has to do with this radio galaxies I already told you in clusters. So this is again an observation of a galaxy cluster with, in X-ray with the XMM Newton satellite here in red, and with the GMRT radio telescope in India, where you see this really complicated, large megaparsec-sized radio structures. And this almost looks like a disturbed radio galaxy. So one other idea is actually that you do not accelerate particles from this thermal ICM, from this hot gas, but you essentially re-accelerate kind of this old particles from these radio galaxies which were moving around in a cluster. And over the lifetime of a cluster, there must be many of these radio galaxies have been moving around. So maybe they have supplied really a large population of kind of this fossil plasma, which you could then re-accelerate. And this should also work for low Mach number shocks. And there are additional kind of variations of this model proposed here. So I said, like, we think that these sources trace shockwave, so I should provide you some evidence that they really do. And there I use this observation of this very nice galaxy cluster here. I already showed some image before. So this is, again, in blue an X-ray image, and in red a radio image. And, okay, something. Okay, it's back, great. Interesting, there's some cosmic noise here. It's probably...
Looks like it might be here.
Okay, I think we're back to normal. Won't touch anything. So this is a really nice image of a galaxy cluster. So it's at a redshift of 0.2, so it's pretty nearby. And the main thing to note here is this really bright, large radio relic here in the north. So here we think that this traces a shockwave. So what is the idea? So again, I zoom here on this radio image here. So this should trace a giant shockwave. So that's indicated here with these arrows, which propagate outwards, as I've shown in this movie, where you have this cluster collision. And when you accelerate these particles at the front of the shock, so that's the idea. And in this case, I, for example, say via the diffusive shock acceleration mechanism. And then in this post-shock region here at the back of the shock, we should have energy losses, because as I already said, like if you have cosmic rays, electrons, they radiate singleton emission, so they lose energy. And that means that we have a very clear prediction that the spectral index should change, and I come to that. So why is that the case? So this is a typical spectrum of a particle which you accelerate. So this is a singleton spectrum. So here we have flux, brightness just, and here we have frequency. So most acceleration processes result in power law spectra. So you accelerate something, you get a power law radio spectra. Then when you have these energy losses, because these particles radiate, then these spectra kind of change. They get curved and they steepen. So that's why I said the radio spectral index should change, because it should get steeper in this post-shock region. And that's directly really what we observe. So this is a spectral index map made between two frequencies, in this case 300 megahertz and 1.4 gigahertz, where you see this spectral index gradient. So essentially this flat spectra at the front, and then this steeping. So again here indicated with this line. So flat spectra in the front from acceleration, then this steep spectra from the energy losses in the back. So this is direct evidence essentially for an outward moving shock wave. At the same time, if we have shocks, you compress the ICM, because that's what the shock do. And that also means that you align magnetic fields in the plane of the shock, and that should cause the radio emission to be really highly polarized, because polarized radio emission comes from aligned magnetic fields. And that's also what we observe here. So this is polarization observations done with a very large array, which show the electric field vectors here, showing that the magnetic field is really aligned with the plane of the shock, and that's what you expect. So this is really good evidence for shock acceleration. Then of course you say, yeah, but I don't see the shock, so we have to go to the X-ray observations. And you can already see kind of the problem here, because we have to measure kind of if there's a shock. So how do we do that? You can, for example, do that by taking two temperature measurements, in front of the shock and in the back. And if the temperature jumps up in the back of the shock, that's evidence for a shock. But there are very few X-ray photons here where you can do your measurements. So this is extremely difficult. And you can, for example, not do that with the Chandra telescope, because it simply does not have the sensitivity to collect enough photons for a temperature measurement in this pre-shock region. For that, I worked together with Hiroki Akamatsu, who worked with the Suzaku satellite. And this satellite has a quite poor angular resolution, but it's extremely sensitive. So it can make this kind of like temperature measurement in this pre-shock region. And here you see what's happened. So he made these temperature measurements here. And then when you hit this radio relic, so this location here, you see the temperature jumps up to 8 keV. So this is evidence for a shock being present in the ICM. And then also you see that we have this counter relic in the south. It's a bit more messy. But also there, we see an evidence for a temperature jump at this location, again indicating the presence of a shock. So this is all kind of gives a consistent picture of particles accelerated at shocks. And this is not the only cluster where you see the spectral index gradient. So I've shown some recent work here from recent observation, where in many cases you see this kind of, these are all this kind of symmetric structures from this binary merger event, where in all these cases you can see this kind of spectral index gradient from the outside to the inside, again indicating that these shocks propagate outwards and this energy losses in the post-shock region. What we also try to do with this cluster is actually try to reconstruct the merger event. For example, there are some basic merger parameters, for example, right? What is the mass ratio of the merger event, and what is, for example, the impact parameter? And for that, again, we use this kind of simple toy simulations here. So these are two simulations. This is a cluster merger with a mass ratio of 2 to 1. I show here the temperature distribution. This is the same mass ratio, but with a different impact parameter. So essentially, an off-axis merger event. And you can see kind of this produces an asymmetric distribution. So we think that by looking at this radio relics, we can actually determine roughly what the merger scenario is. For example, the size ratio and the asymmetry. And the conclusion we had just from radio observations alone, because at this time we had no X-ray observations, we found that there was a 1 to 2 mass ratio merger roughly. Merger axis was really in the plane of the sky. And the merger event was roughly a gigayear after core passage, after making some very simple estimates for the cluster mass. And very recently, actually, we have done also optical observations of this cluster. So observations with the Keck telescope in Hawaii and with the Subaru telescope. So this is essentially the galaxy distribution of this cluster. So one of the things, of course, we want to see a binary merging cluster. So we can essentially just make very deep images and count the number of galaxies. So this is the galaxy distribution, and you really see there are two clumps in this galaxy distribution. So again, consistent, but that this is a merging cluster. At the same time, we can also do a direct measurement of the cluster mass via weak lensing observations. And that's, I show here, that's basically the weak lensing contours, again, consistent with a binary merger event. And then finally, we took spectra of about 150 galaxies to measure their velocities. And that, again, is consistent with a picture of a binary merger event where there are basically two clumps in the velocity distribution, but with a very small difference in the absolute velocity. And that you expect because this merger is in the plane of the sky, and with the spectra you measure radial velocity, so this is what you should measure. And what we find here that this was roughly, so from this kind of like real, kind of more better observations by really looking at the mass distribution, you find this is indeed roughly a 1 to 1 to a 1 to 2 mass ratio merger event. And it's a very massive cluster, so a mass of 10 to the 15 solar masses. So it's one of the most massive clusters actually in our universe. And also from some basic simulations, again, we recovered this 1 gigayear after core passage. So more or less confirming our initial idea from the radio observations about this merger event. Okay, so that were the radio relics, what we have learned the last years. So what do we know about radio halos? They're a little bit more puzzling. And there are essentially two models for radio halos. And this is a little bit technical. So the first, what we have the hadronic model. And here the idea is that galaxy clusters contain a population of cosmic ray protons, not electrons. So protons are also cosmic rays, but you cannot directly observe them because they do not emit synchrotron radiation, or not in amounts you can observe. And if these cosmic ray protons are present, because there are many processes which can accelerate these protons, for example, also AGNs, they can sometimes collide with a normal thermal ion in the medium. And when that happens, you get all kinds of decay products. That's what happens more or less in a particle collider. And in the end, you get from this all these decay products, you get relativistic electrons. And when you get electrons again, you expect this synchrotron radiation. There's another prediction from this model that in this kind of decay process, you also should expect gamma rays. And that you can, for example, detect with the, you can hope to detect with the Fermi satellite. And this produces very powerful type of radio spectra. So this is one model, and there is an alternative model, and that's what we call the turbulent reacceleration models. So the idea is that if you have galaxy cluster merger events, you generate turbulence. So there's a kind of random motions in the ICM. And it turns out that you can also accelerate particles by turbulence. So not only by shocks, but by turbulence. This is, of course, less efficient than shocks because it's kind of messy. But this process, you can produce, we think, these really energetic cosmic rays. And the nice idea about this model, why this is attractive, is that we find these halos always in these merging clusters. So where this turbulence is present, because mergers should generate turbulence. Well, in this model, essentially, radio halos should be found in all clusters, because they should maybe all contain a large population of cosmic ray protons accelerated by other processes. So that's why people more or less favor this model here. And there are other reasons for that, which I come to. So again, I said like radio halos mainly occur in merging clusters. And that I want to indicate one more time here. So if you look at galaxy clusters at the images, so you see two images, one of a relaxed cluster and one of a merging cluster, you see they look quite different. And you can quantify that by, for example, looking at the concentration parameter, plotting that here of a galaxy cluster, and looking at the centroid shift, which is a measure of essentially how asymmetric a galaxy cluster is. And now this is for a large sample of galaxy clusters, and now all the galaxy clusters with radio halos are color-coded in red. And you can see that in this part of the diagram, where the merging clusters live, where most of the radio halos occur. So this supports this scenario that there's maybe a relation with turbulence. It's a very indirect, but that's the idea. And there's a little bit of more evidence, and that is because the turbulent reacceleration model also predicts kind of curved spectra, not power law spectra. This is quite unusual. And indeed, for the brightest radio halo we know of, in the coma cluster, we indeed observe such a curved spectra. This is just one case where we really have detailed measurement, where you can see that this is the power law spectra, but now there's a turnover and it suddenly steepens. And because of this steepening, if you would observe the radio halo here, you see the slope is very steep. So this model predicts that you should find radio halos with a very steep spectrum if you observe them in the right frequency range. And that you don't expect with this other hadronic model. And indeed, we have found a few examples of these radio halo with this extremely steep spectra. So they really are very faint at high frequencies, but get much brighter at low frequencies. So a prediction is now, if we start observing galaxy clusters with low frequency telescopes, we should find many more of these sources, because as I already said, they should be much brighter at low frequencies. And for that, I go to essentially the first new results. And for that, we use the LOFAR telescope. This is an image of one of a LOFAR station. This is essentially a radio telescope, so it looks a bit unfamiliar. And this telescope operates at really low frequencies, and that's important for this work, as these sources have this steep spectra. This is a kind of aerial picture of LOFAR, where you can kind of see the LOFAR stations. A couple of them here in the center, in the core. And you should think of this LOFAR station essentially as it's flat, but it essentially emulates a giant telescope by working in software. So there are all kind of small antennas here, which simulate a giant dish. And it's actually much cheaper, because these giant dishes are very expensive. They're from steel, you have to move them around, you have to paint them very often. Well, it's very cheap. Dipoles on the ground, they're extremely cheap, and you can mass produce them. And also computers are now very cheap, so that really helps. And this telescope has really, another interesting thing is, has really long baselines. So there are many different stations all across the Netherlands, and also even across Europe. And why is this important? Because we observe at low frequencies, the resolution is really poor, because the wavelengths are like tens of meters. So we need very long baselines compared to a frequency telescope at high frequencies to get comparable resolution. And there are actually many challenges with this kind of telescope, because first of all, it's new. We don't know very well how to work with this kind of telescopes, because we have this phased arrays structure. It's also very difficult from a calibration point of view, and I will come to that. And another problem is data volume. We think, okay, why is this a problem? Because we know about big data, but it's really quite challenging. So I show here essentially the copies you can make of the signal. So this thing can simulate, for example, 3 telescopes by itself. And you can even simulate 100 telescopes if you have enough computing power. So this is really powerful. So why is this challenging? Now, if we take a typical observation of a galaxy cluster, say 8 hours, this is very normal, this is what we do, we produce 0.1 petabytes of raw data. So this is challenging. You can already see this you cannot download to your desktop computer. And this costs us a lot of work in the last couple of 10 years to deal with this, to process this, to make it smaller, and to analyze it. For example, this raw data is processed on kind of a dedicated 50-node cluster. It's then kind of averaged down, because otherwise it's still just too large, and then it's sent to an archive. And this archive contains now 30 petabytes of data. So it's all big data, and a lot of the processing has to be done on this kind of computing centers, and that's actually quite challenging. But we kind of can do that now. But there's one, so this is essentially a zoom in of these antennas, of this lower antenna. So here you see this kind of like a tau antenna. So there are two types of antenna, one of them operating in the high band, so that's roughly above the FM band, and there's another antenna below the FM band. You think now, why not in the FM band? Because that's just like mess. You don't observe in the FM band. So you cut that out. So that's why there's this gap between 80 and 110 megahertz. It's just full of junk. You cannot observe there, unless you like to observe other things. So essentially in these tiles, you have simple dipoles. They're just covered with plastic so they don't rust away. So that's why it looks a little bit weird, but they're just dipoles sitting on the ground. And these are these other dipoles essentially here. Just in these wires, there's a dipole sitting, and there's a small receiver here. Then there's a cable going in the ground, and it sends it to this computing, this central processor here, computer. And from there, it's sent to a big correlator super computing center. Now, why is this challenging? This has to do with the ionosphere. The ionosphere is quite a pesky thing. And what happens with the ionosphere, so if you observe at high frequency, like a gigahertz with a very large array in New Mexico, then these radio waves, they just go through the ionosphere and not much happens. So no problem. If you observe at very low frequencies, then essentially the radiation just bounces off. So you're just lost. You cannot observe this radiation from the ground. So that's roughly below 10 megahertz. Now LoVa operates in this regime of around 100 megahertz. And what happens here is all kind of nasty stuff with your signal. So it propagates through the ionosphere, but the wavefront gets really distorted. So it's kind of a nasty signal. And if you do not correct for this distortion, you essentially make very blurry images. And that's what I show here. So this is an actual movie, a radio movie, with a snapshot taken every 30 seconds at the resolution of 3 arc minutes. So why 3? I didn't touch anything, but. Okay, fine. So this is with a resolution of 3 arc minute, and that's comparable to your eye. Actually, your eye is a little bit better than 3 arc minute, but it's kind of a nice comparison. And here I show the moon to size. Now this movie was taken with a quiet ionosphere, and this movie was taken with a more wild ionosphere. And now you can see what happens if I play this movie. What you can see is that there's radio sources here in this wild ionosphere condition, which is actually more typical. This is more, I would say, a normal ionosphere, and this is extremely quiet. This is kind of, you're really fortunate if you observe under these conditions. You see this kind of radio sources, they dance a little bit around. And this is at 3 arc minute resolution, so you could see this with your eye again if you would look at it. So if you want to make images at arc second resolution, you get huge motions. And if you don't take these motions out, you essentially end up with a blurry image. So a lot of work has gone into developing techniques to undo this kind of blurring motions to really make the first sharp images at low frequencies. And for that we developed a new calibration technique. And just to illustrate what this calibration technique does, I show here an image of a famous galaxy cluster, Able 256, using standard calibration techniques, what people have been using for the last 30 years now. And you see you get a really blurry image. And if you run this new calibration algorithm to detect for this ionospheric motion, this is what happens. So essentially you sharpen everything up, and now you can really study this cluster in detail. And this took an enormous amount of work to get to this point, to do this, because it's a really complicated technique. It's kind of a bit comparable to adaptive optics, but you have to, these corrections are really dependent on all over the field. So it's not like one correction you have to make, but it's kind of like a rubber sheet correction almost you have to make. And it's also really computationally intensive, so it's not tricky to do this. You really need powerful computers. So now so once we had this technique under control, the first deep LoVa observation was from this cluster, what we call the toothbrush cluster. You can see why this is here's a bit of a toothpaste like leaking out here. And again, this is like a combination image of Chandra observations, which kind of show this is a really big merger event. So you see a merging cluster here with kind of a bullet sitting here. And you see this giant radio relic in the north. Now, one surprising thing we found from the Chandra observation, that's here, we were looking for shocks, because again, we think that this structure trace shocks. So we did a very careful analysis here to look for the shocks. And indeed, we found a pretty a nice shock in the south. And here you see an X-ray surface brightness profile with a jump here. That's another way to detect the shock, where we found a shock with a Mach number of 1.4. So very weak, but very well detected, also in the temperature. And we were also looking, of course, for the shock here, because this is the bright radio relic, so there should be really a shock here. And this is the X-ray surface brightness profile here, and this is where the relic is. And you can already see there's not a very nice shock present, a very wimpy, maybe a Mach 1.3 shock, or even weaker than that. And that's immediately very puzzling, because we have this huge bright radio relic sitting in the north, and we have trouble detecting the shock. And then in the south, we have some wimpy radio emission here, but we see a very clear shock. So clearly we lack something in our understanding here, like why is this radio relic so bright if the shock is so weak? And again, so this should trace an outward traveling shock is what we think. So we also can look at the spectral index again. And that actually gives a consistent picture. So this is an outward shock. We have the energy losses, and then we see the steepening of the radio spectral slope. Again, this is a spectral index map, green flat, blue steep. So consistent at least. So this probably traces the shock. But then we started calculating the Mach number and compare that to the radio spectral index. And immediately if you do that, you see that this doesn't match. So if you measure it from the X-ray observations, we have Mach 1.3. And if we measure it from the radio spectral index, we find Mach 2.8. So this is clearly inconsistent. These two numbers do not match. And this probably tells us that this prediction from diffusive shock acceleration is wrong. So maybe it's not diffusive shock acceleration which works at this relic. It's some other mechanism. And you can do another calculation. You can look at the energy flux through this shock. So how much energy do you have even available to accelerate particles? And it turns out that you essentially need all of the energy of the shock almost and put that into relativistic electrons. And that does not match the observed radio power of this thing. So there's also a problem there, that the shock does not seem to have enough energy available to accelerate these particles. And then finally, from these lower observations, we also looked at the radio halo. So this was this fainter emission sitting south of it, and we did this very detailed mapping of the spectral index. And what we found is that the spectral index in all these kind of small regions here is really uniform. And this is also puzzling, because if you have turbulence, if this turbulent reacceleration model, you expect that the spectral index should vary, because the turbulence is not constant over the ICM. This really should vary from location to location, and that should be reflected in the spectral index. And that's not what we observe. So here, this is again an open question, like why is the spectral index so flat, and is this really consistent with the turbulent reacceleration model? We don't have the answer at the moment for that question. So going now to reacceleration, because I already talked a little bit about the radio galaxies in the cluster. What role do the radio galaxies play? So just to summarize, we have found a couple of problems with shock acceleration. So the first one I showed you. So the radio relics have very low Mach numbers, the shocks there, but the radio relics are very bright. This seems to be inconsistent. We already saw that there was a mismatch between the spectral index and the Mach number. And there's also other work which actually tried to detect gamma rays from the shocks of radio relics, and they essentially came up with a non-detection, also in conflict what you expect from diffusive shock acceleration. And then finally, I think this is the clearest case. There are also very clear shocks in clusters, but no radio relics. And this was an observation I did with Helen Russell, where we looked at this galaxy cluster Abel 2146. It has beautiful symmetric shock waves here. You can kind of make them up by eye. These are the shock waves here. And then we did a very deep radio observation, because we felt like, oh, now we're going to detect some very nice relic. But we found nothing. So clearly, again, there's something wrong with our picture here. So there's some ingredient missing at least. And that's where this cluster comes into play. So this is the galaxy cluster Abel 3411, 3412. It's essentially a giant version of the bullet cluster. This is a giant bullet, so it's a very violent merger event. Essentially a binary merger event happening along this axis. And it's again located relatively nearby, so at redshift of 0.16. And this is the combined Chandra GMRT. GMRT is a big radio telescope in India, which can also observe at low frequencies, mainly at the 600 megahertz range. This is a combined Chandra GMRT and Subaru image in the background here of this galaxy cluster, where you see essentially this very complicated radio relic sitting here in the south. And the interesting thing is, if you look in a little bit more detail at this radio relic, if you look, this is again like showing this is a binary merging cluster event. These are Subaru observations showing the galaxy distribution. So you see basically two subclusters merging along this axis. And Will Dawson worked on this, also did modeling of the merger event, so roughly determining the mass and the time since core passage. So again, this gave us confidence in the picture that we roughly understand the merger event. But now there's one interesting thing. If you start zooming in onto this part of the relic, what you see actually here, that there is an AGN sitting here, a jet coming out of the AGN, which then ends up in the relic. And we have evidence for a very weak shock at this location. You can kind of see it in this Chandra X-ray image here. And this is the X-ray surface brightness profile here, which indicates a very low Mach number shocks. So we see a jet coming out of a galaxy from the supermassive black hole. And then the jet somehow hits the shock waves. And then something special happens, what we think. And how do we know that? That's by going to the radio spectral index. So again, looking at acceleration and energy losses. So we have a supermassive black hole sitting here, in this galaxy here, which accelerate particles. So we have flat spectra, green. Then we have this tail, where we have the energy losses, because the particles are accelerated in the black hole, then they stream out, and the spectral index steepens, so it gets blue. But then something special happens. When it hits this kind of shock wave, which we detect in X-ray observation, then suddenly the spectral index flattens again. So this is essentially evidence for re-acceleration of particles. So it seems that there is actually a close relation between these radio galaxies and these shocks, that essentially the shocks can re-accelerate plasma from radio galaxies, at least in this case. And this is the polarization map, again, showing evidence for this shock compression. And this is evidence for, essentially evidence for re-acceleration. So maybe we do not accelerate particles from the thermal ICM, but we re-accelerate this old kind of cosmic ray electrons in the tails of radio galaxies. And that's also what there's a compilation of LOFR observations show. They show essentially the presence of a large population of this kind of steep spectrum radio sources in galaxy clusters. Now, finally here, going to the frontier fields. So we also work here at CFA on the frontier field clusters with Chandra. They're very interesting clusters because they're extremely massive and they're all merging. And that's why I was interested in them, because merging clusters, again, should be particle acceleration. So we did some really detailed studies in one case of this cluster. So that's one of the frontier field clusters. That's, where is it actually? Here, MaxTeo 717. It's actually the most messy one of them. It's really disturbed. It's kind of a mess. And we think it's a merger of at least 4 different clusters. So not a binary event, but 4 different substructures. And that's why it looks so complicated. There's a lot of interest in the cluster because it's so massive. So it's also the largest known cosmic lens. So people really like this cluster to look at lens radio galaxies, to look at background sources. But it's also an extremely violent merger event, and that's why I was interested in it. So this is the combined press release image that was made, which shows this kind of really complicated merger event. So we have a radio relic sitting here. This is the X-ray emission, again in blue. And then we have a 4-count radio source here. These are just jets from an AGN, and this doesn't belong to a cluster. So it makes it for a nice picture, but this is a 4-count structure. It's unrelated to the cluster. It's not a radio relic. And the interesting thing is that if you look in the center of this radio relic, you again find this radio galaxy here, sitting at the galaxy where 2 jets are essentially coming out and resulting in this fossil plasma. And this is a deeper radio image showing additional diffuse emission all the way in this entire volume of the cluster. So this is a spectral index map of this radio galaxy here in the center. So this again, I think, is evidence for re-acceleration. So here we have the supermassive black hole. The jets comes out. The jets are bent because the galaxy is moving with high velocity. Then we have the aging in the jets, and then the spectral index flattens again. The only thing what we could not find here is evidence for a shock. So we see evidence for extremely hot X-ray gas, indicating the presence of some kind of shocks, but we could not find any like surface brightness edges or something. Probably because this thing is just a train wreck. It's so messy that we could not really identify where the shock exactly is. So this was the hottest regions here. And this was a temperature of above 20 keV, which is extremely hot gas. So this is a summary. So I've told you that galaxy clusters are really the largest particle accelerators we have in the universe that we know of. And that is radio halos probably trace ICM turbulence, but there are still a lot of open questions for radio halos. And that radio relics trace merger shocks, that's quite clear. And we think that at least for a subclass of radio relics, the particles which are accelerated come from the tails of radio galaxies. So they're not accelerated from the ICM, but we essentially re-accelerate particles. And this maybe solves this mystery of why these very low Mach number shocks can accelerate these particles so efficiently. And then finally, this LOFR observation showed this the presence of steep spectrum fossil plasma actually in quite a larger number of clusters. So what can we now do? What do we have to do in the future? So how can we make progress? So the first thing is that I showed just a few specific examples. And what we actually want to do is we really want to study this in a large sample of galaxy clusters to essentially determine how does, for example, the diffuse radio emission and the particle acceleration evolves over cosmic time. How does it scale with the mass of the cluster and the dynamical state? And for that we will use LOFR. And the good thing is that we already have this very large X-ray galaxy cluster samples available. And that's a project here at the CFA. That's the Chandra Planck cosmology sample, where this is a small subset of the sample, where Philippe and Christine Jones are working on this. And the idea is now to observe this sample with LOFAR. So this is a compilation of all these clusters. You see many merging clusters, and also relaxed clusters. So how will we do this? So here we will make use of the LOFAR all-sky survey. So LOFAR is now doing a survey of the entire northern sky. That will be 3,000 pointing in total, each of 8 hours, and each producing 0.1 petabytes of data. So this is, you see where the challenge is, that's the data rate. At 5 arcsecond resolution, and this is the progress, all the red pointings we have observed. So we still have a way to go, so we roughly are at 15% of the sky done. And this is mainly essentially limited by this data rate, so we're working on that, improving that. And Tim Schimmel is leading this effort. He's in Leiden. So this survey will be an enormous improvement over previous work. So here I plot some kind of the old radio surveys as a function of frequency and sensitivity. And the size of the circles is proportional to the resolution. So a very small size means a very good resolution. So big is not good, it's bad, it's blurry. So here's where the LOFAR survey is sitting. So you see this really good resolution, and you see essentially a 2 orders of magnitude improvement over this previous survey. So this will be an enormous step forward, and we should basically find hundreds of clusters, new clusters with radio emission. And this is just an overview of a few test pointings. So from this lot survey. So it's impossible to show this properly because this image is just ridiculous in size. So this is already 20,000 by 20,000 pixels. So you need a really good projector to show anything. And I just show some zooms in here from interesting sources out of this survey. So you can get an idea, like, even from a few pointings, how rich this is. And essentially each of these observations is comparable to the deepest observation we have ever taken in this frequency range. And now we'll do this essentially for the full sky. Then the final thing what is very interesting is, because I showed you radio emission from galaxy clusters, but I already told you the galaxy clusters are embedded in the cosmic web. And there should also be shocks in the cosmic web. This is a simulation from Franco Vaza, highlighting the shocks in this cosmic web. And this cosmic web accretion shocks, so the shocks in clusters have very low Mach numbers here in blue. So these are cluster shocks, color-coded in blue. But in the cosmic web, the shocks have Mach numbers of like 10 or higher. So these shocks should also accelerate particles. Now the problem is that densities in the cosmic web are extremely low, so the radio emission will be very faint. So you need like a really good telescope to be able to detect that. And why is this interesting? If you can detect radio emission from the cosmic web, you can measure the magnetic field in the cosmic web, because again, radio emission is like cosmic rays and magnetic field. And if you can measure the magnetic field in the cosmic web, that says something about the origin of our universe magnetic fields. So these are two simulations for different origin of magnetic fields, and they're basically two classes of models. So one of them is an astrophysical model, where you say magnetic fields were essentially generated by outflows in galaxies or AGNs, and that's how magnetic fields populated our universe. There's another model where that says magnetic fields are generated during phase transitions, really shortly after the Big Bang. And these are simulated radio maps of the cosmic web for these two different models. So if we can detect the radio cosmic web and look how essentially the brightness distribution of this, we can attempt to distinguish between these two big models for the formation of magnetic fields in our universe. And the idea is to use very deep LOFAR observations and future observations with a square kilometer array, which is kind of the next generation of radio telescopes after LOFAR. And the future is here really bright, because I said in the radio there's an enormous amount of new telescopes coming online. This is just a collection of them. Some of them look weird, because these are all these kind of phased array telescopes, so they're kind of these cheap antennas, but they're really powerful. So these things should all in the next 5 years should come online, and should basically, and this is all enabled essentially by advances in IT technology, because it's all about data rates essentially to pump this, and electronics. So there's an enormous amount of progress being made here. And also in the X-rays there are plans to do better missions than Chandra and XMM. And then the exciting thing is with these new missions which are proposed, such as Athena and the Lynx mission here at CFA, that you could do direct measurements of ICM turbulence and also of velocities to test essentially this turbulence reacceleration measurement. You could also do very precise shock measurements, and you could also attempt to directly detect this non-thermal electrons via line ratios, for example. So this could be directly detectable if you have high spectral resolution. So this would be really exciting times ahead in this field, given what's coming, especially in the radio, more or less already now, and in the next 10 years what will come in the X-rays. Okay, I'll end here. Thank you.
So I want to thank you, and thank you for maintaining your poise despite occasional interruptions. So this talk is open for questions.
Two quick questions. That image of the AGN blasting into the radio relic, like it seemed almost too good to be true for confirming reacceleration. Is that the first obvious observational evidence of that?
That was the first one, but then after that I showed the next one. So we actually have a couple of cases. This was the best case, but we have a handful of like more dodgy cases where initially we thought like, okay, maybe too good to be true, but then we saw this case and said like, oh, now everything works out and works together. So yeah, so that's the best case, but there are more.
Okay. And the other quick one is, how can you weave Sunyaev-Zeldovich observations into the story?
Absolutely. So another way to detect shocks is by Sunyaev-Zeldovich. And the interesting thing here is that if you have a good enough SZ telescope, you can attempt to detect shocks very far in a cluster outskirts. That's because the X-ray emission goes with density squared, but in the SZ it's more or less proportional to the pressure. So in that way you could maybe make accurate shock measurements in outskirts. So yeah, that's a very important thing, and people are attempting that. The challenge is get sufficient resolution with these SZ observations. Because the shocks are, of course, sharp things, so if you have like a arc-minute resolution, it's all blurred out.
Gary.
With regard to that point, these shocks presumably are exciting and ionizing different atoms. And is there any possibility of detecting them in the optical or near infrared? Or are they just too faint?
I think they're simply too faint, but with new X-ray observation, actually, it is interesting to look at ionization, for example, ionization balance after shock, which will change after a shock. So if you can detect lines in the X-ray, which we cannot do at the moment, that is kind of like high resolution and sensitivity, then you should also be able to detect the shocks in this way. Yeah. By using, for example, line ratios.
Yeah, it's a standard technique
Yeah.
in the optical infrared.
But the problem is that ICM density, we have a 10 to the minus 4 particles per cubic centimeter. And it's extremely hot gas as well because it's 10 to the 8 Kelvin, so optical is not.
So I want to ask about, so let's say you take those radio relics, those shocks, you're basically assuming we're the edge on looking at those shocks. What if like we are face on or a little bit 45 degrees? Can you still measure the Mach number accurately?
That's a very good question actually, and that's one of the troubles we have. That is the projection effects. And that's why I showed, in this case, I showed you most cases where we know the projection effects are quite small, because if you orient this kind of things in the wrong way, it becomes really messy and very difficult to do these measurements. Yeah, so projection is always a worry, and it's always quite hard to deal with. So that's, there are 50 other clusters with diffuse radio emission, but in many of these cases, the projection effects are unfortunate, and it becomes too complicated to learn something. Yeah.
So actually, I'll take a follow-on to that question. Because quite a few of those features you showed were really looked on the screen like a very sharp line. Right? So that must give you some sort of sense of the degree of limb brightening you're getting at a curved shock. Does that give you any geometrical information that's useful?
Yes, actually we have used this kind of thing to figure out what the projection effects roughly are, because the sharper, the more edge on, and it also says something about the extent of the shock plane along the line of sight. So yes, we are using that information.
You have mentioned dark matter in a cosmological talk, which is quite remarkable. My question is about this. This data from the LOFAR survey is going to become public anytime soon?
It's already public, a lot of it. It's public after a year of observations like any other major observatory.
Ah, okay.
But you want to download it, that's
Actually, I have a question about the correction for ionospheric turbulence. Does that depend on having pre-identified point sources in the field, and you just use those as markers in a similar way to adaptive optics in the optical infrared?
Yes, exactly. That's how it works. So every field has like hundreds of bright sources. We essentially measure very precisely how these sources move, and then essentially we use that to correct them. So. And where these sources are, we kind of first make an image, a bad image, and then we already know where the sources are, and then we use them kind of anchor points to essentially fix this kind of and build this. Is
there some sort of characteristic angular scale in the problem? The
yes.
equivalent of an isoplanaric patch?
Yeah, there is, and that's actually one of the main challenges, because I showed you all observations at like 150 megahertz roughly, and this patch gets smaller and smaller when you get to lower and lower frequencies. So what would be really interesting is to do low for observations, say at 30 megahertz. But then the problem is that the patch gets too small and we do not have enough bright reference sources per patch, and then the correction kind of doesn't work. So this is really relevant, yes. We need kind of guide stars,
Yes.
the equivalent of that in gradation.
Well, you have to create your own beacons, right? And there might be another problem. So, there are no further questions. Let's thank our speaker again.